Okay, so in example 4, we are going to use synthetic division to divide by x plus 1. We'll put a negative 1 on the outside, and the remainder, by the remainder theorem, will be negative 1. So over here I have that worked out. We put the coefficients of the polynomial, 4, 7, negative 6, 1. We have to put a 0 for the placeholder for the x, negative 8. Alright, we're going to divide by x plus 1, so we put the opposite, the negative 1 out here is the way synthetic division works. That way we can add the columns instead of subtracting. So we drop the 4, multiply times negative 1 to get negative 4. We add to get 3, multiply times negative 1 to get negative 3. I add to get negative 9. Multiply negative 9 times negative 1 to get positive 9. Add the column to get 10. Multiply to get negative 10. Add to get negative 10. Multiply to get positive 10, add negative 8 plus 10 to get 2. So by the remainder theorem, p of negative 1 should be the remainder 2, and we have the quotient here, 4x to the 4th plus 3x to the 3rd minus 9x squared plus 10x minus 10. Okay? If you look back over just to verify that, p of negative 1 equals 2, if we look at the original polynomial, if we plug in negative 1, we're going to get negative 4 plus 7, which will be 3. The negative will make this become positive 6. 3 plus 6 will be 9. Plus 1 will be 10. Minus 8 will be 2. So if you actually plug it in and evaluate it, p of negative 1 does equal 2 to check out the remainder theorem. Okay, we just have 2 more slides, a couple more problems. The factor theorem says that c is a 0 of p of x if and only if x minus c is a factor of p of x. So that shouldn't be too surprising. We know that to find the x-intercepts, the zeros of the polynomials, that we factor set each piece equal to 0. Okay. So the proof, you have to prove it both ways. You have to prove first that if c is a 0, then x minus c is one of the factors, and you have to prove that if x minus c is a factor, that c is one of the zeros. Okay. One way is really easy. If x minus c is a factor, that means p of x is x minus c times some quotient q of x with no remainder. And if you plug c into that, you're going to get 0, because if x minus c is a factor, then you're going to have 0 times something is going to be equal to 0. The other way, if p of c is equal to 0, well, the remainder theorem then says, together with the division algorithm, that we'll get p of x is equal to our divisor, x minus c, times the quotient plus the remainder of 0, which shows us that p of x is equal to x minus c times q of x, or in other words, x minus c is a factor. So, just a formal mathematical proof that x minus c is a factor if and only if c is one of the roots. That helps us do problems like 5 and 6 here. Number 5, we're going to find a polynomial with roots 1, 2, negative 1, and 1. Well, by our previous theorem, if 1 is going to be one of the roots, x minus 1 is going to be a factor. If 2 is a root, x minus 2 will be a factor. If 1 is a root, x plus 1 will be a factor. X minus minus 1, x plus 1. And if 1 is a root twice, then x minus 1 will show up twice. So here I have example 5. The polynomial, I could do any multiple of this, but one polynomial that would work would be x minus 1 times x minus 2 times x plus 1 times x minus 1. And then I have to multiply all of that out. I did x minus 1 times x minus 2 here first. I FOILed it out, got x squared minus x minus 2x will be minus 3x, and then plus 2. And then we have the difference of squares. X plus 1 times x minus 1 is x squared minus 1 squared. X squared minus 1. And then I multiply all that out. I do x squared times both terms. X squared times x squared gives me x to the 4th. X squared times minus 1 gives me negative x squared. Then I move on to minus 3x times both terms. Minus 3x times x squared gives me minus 3x to the 3rd. Minus 3x times minus 1 gives me plus 3x. And then finally, 2 times x squared gives me 2x squared, and 2 times negative 1 gives me minus 2. I combine some like terms. We have the 1x to the 4th, minus 3x to the 3rd. We have minus x squared plus 2x squared, that'll be plus 1x squared, and then 3x minus 2. So the simplified answer that we want is x to the 4th minus 3x to the 3rd plus x squared plus 3x minus 2. We're going to have one more, example 6, which is here, but let's go back and see what the problem was. Given that x equals 3 is a 0 of this polynomial, find the other zeros. So what I'm going to do, since I know it's a 0, I can do synthetic division and find the quotient. The remainder will be 0, which will be a good check on our work, and we'll find the quotient and be able to use that to factor and find the other zeros. So I start with synthetic division. I use 3, the potential root, put the coefficients, add 1, negative 14, and 24. I drop down the 1 and then multiply to get 3. I add negative 1 and 3 gives me 2. Multiply to get 6. Add negative 4 and 6 to get negative 8. Negative 14 and 6 to get negative 8. I multiply negative 8 times 3 to get 24. To get negative 24. It didn't quite show up on the scan there. This one's a negative 24. 24 times negative 24 is 0. So that tells me that I got a remainder of 0. So the original polynomial is equal to x minus 3, because that's what we were dividing by, times our quotient, 1x squared plus 2x minus 8. And then I further factor x squared plus 2x minus 8. I need two numbers that multiply to be negative 8, negative 2 and 4, add to be 2. So it factors this way. Set each equal to 0, I get x equal 3. Set x plus 4 equal to 0, I get negative 4. Set x minus 2 equal to 0, I get x equal positive 2. And there we go. That's the end of section 3.2. We'll talk about it more in class.